Okay, our first speaker here on Saturday afternoon is Don Smith. Don hails from Texas, and he came up to the Tesla Symposium last year for his first time and was kind of an unscheduled, unexpected kind of person there, and showed us some very interesting ideas in free energy type motors. He's been working on this for several years, and he's now in a position where he's ready to present some of this to the public. So let's welcome Don Smith.
Doesn't show up very well, does it?
I don't know if they're feeding the camera.
Have to take it off transparency.
It's probably easier. It's easier there. Okay, I'll get you.
Okay, what we might do is dim some of the lights.
There you are. Okay, yeah, we'll get the lights.
And we also need to know how to turn this microphone on. Is the microphone on? Can you hear me okay? No? Okay, that means this one's not on. Okay. Okay. Okay, we need to probably turn that light down or off. So what it does, it blocks out this.
Yeah.
Are we working in?
Yeah, point at the projector on the screen. There's a little pointer on the podium.
Okay, that light there blocks out the screen completely.
Battery there. Let's see where the battery is.
They're switching channels over here, A to B. From B now. Go ahead and say something, Don.
Okay, is it working now? Is it working now?
Just use the podium microphone to get this worked out.
Okay. Okay, this one's working okay, isn't it? Okay, we'll see what we can do then. There's going to be an awful lot of questions about some of the things that we're going to be talking about, and most of them are contained in this booklet, which they have out in the bookstore. And there's some schematics and a lot of other things in there, formulas and things which are useful in building this type of device. So with that in mind, we'll see what we have next. Basically, energy, all energy, electrical energy comes from electrons. So in the case of electrons, it's all negative. So it's either more negative or less negative. So in the case of electricity, now in case of chemically derived electricity, it's a different deal. But in the case of electrical power generation, it's all going to be electrons, and the electrons are all going to be negative. So basically what we're doing, if we have ambient, which is background, which where you're sitting is perhaps 200,000 volts per square meter, anything above or below that is going to be useful energy, because the electrons, just like the snowball that you put on top of the hill and you roll it down the hill, it's trying to get back to the gravitational level which it was before you put it up on top of the hill. Well, if you raise the electrical potential above the background, it's always going to try to go back to the background level. And it's the in-between part there that's useful to you, and it can either be below ambient or above ambient. So anytime you have electrical energy, in most cases it's going to be above ambient, which means it's above unity. So if you're talking about over unity, all useful electricity is over unity because it has to get back to ambient, which is background. And your over unity people won't be real happy with that thought, I'm sure. We'll give you a clue as to one of the very early things which I saw which got me involved in this type of thing. I'm a geologist by background and work with electromagnetic maps and locating oil deposits, mineral deposits, and other sorts of things. Of course, that's a direct reflection of the electrical characteristic of the earth and our portions of the earth. So that got me involved in electricity initially. I've had a lifelong interest in it. About 7 or 8 years ago, when the petroleum industry went sideways, I had a lot of extra time, and I was asked by the local school system to help out in their science courses. And of course, when you look at the physics books 50 years after you saw them the first time, or you had them in college, you see things which you probably didn't see the first go around. You've had some life experiences, and you begin to see how these things all fit together. So it became quite obvious to me that there were some real big holes in the way that electricity was being presented. Now, one of the early on things which I found was this, and it's from a science supply.
I'm going to play mugger and get this off.
Okay.
Can you pull it off your belt there?
Yeah.
Okay.
The initial device that I ran into was from a science supply house, and it turns out that this company is still around and still makes these things, and I'll show you the actual device. Okay, what happens here, the larger one up there would be like this. The smaller one would be like this. And basically what you do, you put a 1.5 volt battery in this bracket thing here, and it causes this cell to react, and in turn this one is tuned so that it matches this one. Now on this one you put a 70 volt light bulb, and this 1.5 or 70 watt light bulb, and this one with the 1.5 volts transmits the effect that causes this coil to react and generate electricity. The electrons from here are not coming here. They're actually talking to the electrons here and cause this device to generate useful electricity. So you're not diminishing the battery here by running the light over here. So if any of you are interested in knowing all the formulas that you need to know to understand this sort of thing, this kit comes with a 9-page front and back instruction sheet, and it's got all the formulas related to resonance in it and how that can occur. So this thing should tell you immediately that there's something wrong with the way electricity is taught, because you've got 1.5 volt battery here, which is causing this coil to resonate, which in turn is causing this one to resonate. None of the electrons from this electrical system are coming over to this electrical system, yet this electrical system is lighting a 70 watt light bulb.
I think we got your microphone.
Yes. So that should tell you immediately that there's something not quite right. And if you start digging from that perspective, it turns out that there's a lot more to it than that, and it's all good as far as what you might like to see happen. And whenever we get into the Tesla, building the Tesla coils, this is working okay now? Okay. When you get into building the Tesla coils proper, basically what you're doing, you're energizing a smaller coil, which is your L1 coil, and causing a larger coil, which is your L2 coil, to react. And it's the exact same system there, except that it's put into a more compact and convenient system. Now normally the L2 coil would be some distance, maybe 3 times the diameter of the L1 coil would be 3 times the diameter of the L2, but that's not really necessary. It can be smaller than. Now, one of the problems that people run into in building these things is getting the 2 coils to react with each other. You've got to have them so that they can talk to each other. So if you use like quarter wave system, your shortest wave will be the longest length of wire, and your shortest length of wire will be your higher frequency. So with that in mind, one of the problems that people run into immediately is tuning those things. Now, I'm going to show you in a little bit a slide that shows this exact same thing from 1893. It was one of the, in the early radio devices, how they were able to tune them fairly easy. So this is your L1 coil, L2 coil, and the way we're going to do this is PVC, and I cut a collar here so that I could slide it on there and use it for a spacer and put another one there as a spacer, and the net result is that this thing fits almost perfectly. It slides in and out of this particular coil here. Now, this is one way to tune these things without having to figure all of the other characteristics that have to go into it, which gets pretty complicated sometimes, and especially because resistors, although you think resistors are resistors, if you take your LCR meter and you measure the capacitance and the inductance of almost any resistor you're going to run into, you'll find out that the resistor is a lot better capacitor and a lot better inductor than it is a resistor. And those things vary considerably from one resistor to another, and the only way you can get around that is get non-inductive, non-capacitance resistors. And I can tell you, if you go to people who have been manufacturing resistors for 50 years, they won't know what you're talking about. You will have to find the sources pretty much on your own. They do exist. Radio Shack has a few non-inductive and non-capacitance resistors. Very few, though. And they're marked. So don't expect to walk into Radio Shack and tell them that that's what you want, because the people that work there won't know what you're talking about. But if you look on the packages, you'll see that there's a little square box, ceramic box looking deal that says on the top of the package that it's a non-inductive resistor. Now, if you're trying to tune these things by changing the resistance or the capacitance and you're adding these things in, you get into a situation where every time you get one thing corrected, you've got something else out of balance. And the net result is it doesn't work very well. Now, last year, a lot of people have tried to build the circuits which I presented last year, and several hundred people that I know of that have tried to do it. There's only about 6 out of all of those that were able to actually get it done. And I'm not quite sure how they were able to do it. Some of them I know the details and some I don't. But using this particular system here, you can correct for a lot of things that otherwise you're going to need an engineering degree to figure out probably. So this will simply go to your high voltage source. Okay, if you want to build a nice coil, Barker Williams makes a large variety of these coils ready-made, and they're copper and they've been dipped in stannous chloride, which tin plates them, and that's how you get the pretty tin plate. They've used a heat process to embed them in Lexan slits of Lexan, and that's what the ribs are made out of. Now, if you want to make a real pretty Tesla coil, this happens to be the cap off of a sewer pipe. And they come in all sizes from about a couple of inch and a half up to over 25 inches. And if you look at it this way and you see this square thing on the bottom, the square thing on the bottom you can screw onto a piece of board or something very nicely, and you can wind your L1 coil very nicely. See the grooves on it? And it will stay exactly where you put it. And you can use some little clear ties and run a hole or two through it where you can run your ties through it, and all of a sudden you've got your very nice L1 coil, see? And this being a PVC, you can further take a piece of PVC pipe that's been cut to the proper length, and you can set that thing on it just like that. You can use PVC glue if you want to and glue these two pieces together, and then you can take your center coil here, minus the orange one in this particular case. And you've got a very nice Tesla coil, almost ready-made. Okay, if you want to get into amps and other sorts of things, then we have to start using larger wires. And it's the flux lines that are reacting with these particular coils, the magnetic flux lines that are transferring the energy from one energy triangle to another. And if you get into heavy amperage and that sort of thing, this is welding cable, and it comes in all sizes. This happens to be number 8 welding cable, and it will make a very nice high amperage type coil for your L2, and then you can use even larger or copper tubing for your L1 coil. Okay, since we know electrons are a source of electrical energy, electrons do a lot of things. We get a lot of different types of energy from electrons, and I'm not sure whether you can see that or not. Yeah, dim those lights some if you can. Is that better?
Getting better.
You're getting better? Oh, can you see it? Okay, it turns out that electrons provide us with a lot of things besides, say, electricity. And this is sort of a brief breakdown on it, and there's probably other types of things that they provide us with also. But in the systems of storage there, for example, your capacitors would store the electricity, and your coils or your inductors would store the magnetic field. And you've got equal amount of each. Anytime you have electricity, it's a two-sided coin. You have equal amounts of each. There's no way around it, because when the electron moves forward or is disturbed, it's going to give off magnetic energy. When it pops back to where it was, it's going to give off electrical impulse. So you're going to see both of those. Yeah, I have a number of other slides, so we'll need to look at them. Okay, you're familiar with the power triangle and how that works. For example, here, the power triangle system 1 there is your L1 coil, and your L2 coil would be the power system 2. Now, the electrons are not moving from number 1 to number 2. As you noticed a while ago, the L1 coil is covered over with plastic, and that's just fine, because we don't want any of the electricity to be jumping around or sparking or moving. It's the magnetic flux lines that we're interested in. So in case of conventional energy, we've got atoms A and B there, and A would be your volts times amps. That's what's inside the wall before you turn the switch on. When you ground it, then you've got time which comes into it, which would be your volts times amps times time, which you've got watts or useful energy at that point. That's the conventional way of doing electricity. Now, on C there, we have resonant energy, which is not actually going anywhere or doing anything except that it's resonating, and in the process of resonating, it's creating lines of magnetic flux. And your electrical people will tell you that number C there is wattless energy or useless energy. What they're not allowing for is the fact that at resonance you have a tremendous intensity of magnetic flux lines which will transfer beautifully over to another electrical system. And that's what's happening between your L1 and your L2 coils. Now, once you get your L2 coil going, it's going to be moving from the base of the coil towards the top of the coil. As the magnetic flux starts building on each turn there, it's transferring over to the next turn, and it's carrying with it what it had, and it's multiplying by the number of by the flux lines that are being active there. So you're getting an amplification of the magnetic flux lines. These magnetic flux lines are building in intensity as they go towards the top of the coil, and they reach their maximum at or near the top of the coil. Now, at that point, you've got high voltage with not a lot of amps, but the amp business is not going to be a problem for us because we're not going to be using the system that we have at the top there. We're only going to be using the lines of magnetic flux. And in a system which I'm going to show you in a little bit, there's a Tesla's third coil which comes into play, and it acts like the little receiver that did the light bulb thing that I showed you earlier, and it is situated in the highest density of magnetic flux, which means that it's reacting like a power system 3 there, and it's got the benefit of the resonant energy that's been amplified to a very high level. So at that point, what's transferred over into it becomes an entire separate electrical system. None of the electrons have ever actually gone from the L1 to the L2 to the L3. It's the magnetic flux which is reacting with the different coil systems, which is powering the next stage on, or the next layer of turns as you go towards the top of the Tesla coil. Now at this point, you're free of the power system that was present at the beginning of your experiment. And you've got a whole new power system with a whole new bunch of lines of magnetic flux which did not exist previously, and therefore you have gained in energy potential. And your potential at that point, you have a lot more energy than you ever had when you first started out. Now, if we look at the law of squares and the Fibonacci series and other things in nature, for example, if we take the beginning of a human being, we have one cell, and then we have 2 cells, then the 2 turn to 4, and 4 turns to 16, and after that has happened a few number of times there, you've got 1 million things going for what you had initially just one of. And the same thing is true in the case of flux lines. And the flux lines are actually what will give you your energy back, because they translate back into the energy system as electricity. So we will get you some more overhead things in just a moment here, and see how things go from here. Okay? They don't necessarily have to be very close at all. For example, if you have a resonant system, Of course, the flux lines are determined by the square of the distance from the source, so they're diminishing in value as you move away from the device. So it's probably better if they're within a relatively short space if you want to benefit 100% from the flux lines that are there. However, with a resonant system, the flux lines will give you your energy that's totally separate. See, none of the electrons from the original system are actually present in the second or third system. So if someone tells you that what you get out depends on what you put into it, once you've generated those flux lines, well, you're into a different language system which will translate back into electrical energy, and since you have a lot more of the flux lines, you have a lot more potential than you had to begin with. So this law of square business, you see it, anything that's nonlinear. For example, in the when Galileo had his first two laws of motion, and of course he got rewarded for his effort, because you don't go around saying that the earth goes around the sun and things like that. So they held a barbecue in his honor, and you know the rest of the story on that. But anyhow, we go along to Cambridge University about 100 or so years later, and we have farm youth by the name of Isaac Newton, who's studying mathematics, who's not a very good student, and he gets in a fight one day with one of his friends, and something about his whole chemistry changed after that, and he became very competitive and a very good student. And of course, while he was studying mathematics at Cambridge University, he came up with the third law of motion, and then they renamed the whole system to the kinetic energy system, and the rest is history. And some time later, a fellow by the name of Albert, a clerk in the patent office, decided to paraphrase it, and he came up with EMC squared. And of course, he got the Nobel Prize for his paraphrasing of the kinetic energy system. And with that in mind, let's see what else we have. We have all kinds of things to talk about. Here's a drawing showing what happens with the lines of magnetic lines whenever you start getting additional ones. And it goes to millions in just a very short period of time. When that thing flips over very few times, it's into the millions of flux lines. And at that point, you can disturb an awful lot of electrons. And that's what it's all about. Your magnetic flux lines will translate into electrical flux lines and that sort of thing. And then if you've got your coil system where your henries and capacitance and that sort of thing are all working for you, and you know how to hook into it, well, then you've got a lot more energy than you started out with. And there's no doubt that it works. There's all kinds of evidence for it. Okay, getting into the formula for finding what type of useful energy is available to you through this system. This will give you a little bit of an idea. And Joule was a English brewmaster who had all kinds of machinery that ran on steam and some electrical and this and that, and he had to come up with a system which would make translating one system of energy to another more universal. So that's how he comes into this. A joule is 1 volt times 1 amp times 1 second, which is a watt second. That also happens to be the definition of a coulomb and a whole slew of other things. So anyhow, these things all translate in and out of each other, and Joule was the one that came up with the system, and that's where we got the name Joule. So, okay, let's see what that can do for us in the case of a Tesla coil. Say that we have a Tesla coil that is running at 100,000 volts. Well, you might say, well, we're not going to get a megawatt out of something like that. But what happens is it's the cycles per second that come in on that. See, you remember a watt was 1 volt times 1 amp times 1 second. So if this thing repeats itself many times per second, then you have automatically got a lot more than 1 watt there. So this explains how 100,000 volts can become a lot more energy than, say, 100,000 volts. And what you have to do in order to collect this energy is that you have to have capacitor banks to collect it for you and store it temporarily in order to get on to the next stage. Because if it's not in a useful form, it doesn't really mean anything. Okay, you notice on this that we're going from 100,000 volts to into the hundreds of megawatts. And of course, the system has to be built to contain or to operate safely at whatever level it's operating at. But if you've got proper construction for 100,000 volts, you can pump forward many megawatts of energy. And I might say that Hoover Dam is approximately 500 megawatts, and I'm showing here that you can approximate Hoover Dam with a unit which will sit on your coffee table. And this hasn't been actually done yet. I've done it in at a certain level, and I know that it will probably work at that level. And I'm in the process of building a larger units with the welding cable that goes up to about a size 2 or even a 0. And the way you do that, you use some of the technology. If you were going to build yourself your own welding machine, some of the mechanics that are involved in building a welding machine are also involved in building one of these things that will have very high amperage. I'm going to show you some devices in a little bit that they're related to this that have many thousands of amps, plus say 1,000,000 volts at 3,000 or 4,000 amps or something like that. So how many megawatts is that? Okay, I'll let you look just momentarily at the some of the benefits of this particular system. And while you're looking at that, I'll get some more things for you. Is it okay to go ahead? Anyhow, this is in one of the books. Okay. Thought you might like to see what some of these systems look like. The one that you see there on your right, that's a 12-inch PVC sewer pipe. The top piece is about 16 inches long, and the bottom piece is exact duplicate of the top piece. The center device there is a Rubbermaid oil barrel dolly with the rollers taken off of it, and it turned out to be 25 inches in diameter, and it worked out just fine for the L1 coil. And below you see a power system. I'm going to center it now so you can see that power system a little bit closer. What you're looking at here is an automobile ignition coil. And what you're looking at there, where the 12-volt electricity comes in on that connector block, basically I've used a timing circuit which is very common. You take a capacitor with a resistor shunt across the legs of the electrolytic capacitor, and you run electricity through it. You're going to end up with a timing deal. It's going to be cutting it off and on. So it's the resistance times the capacitance of the capacitor that tells you how many times per second this particular ignition coil is coming off and on. Since it's an automobile ignition coil, it runs at 12 volts. The timing system is set up to match the timing system which it normally accepts. If you have an 8-cylinder automobile and you have 2,000 RPM on the automobile, and that'd be 8 times 2,000 would give you your number of times per second this thing is going off and on. So, and also your automobile ignition coil is made to last for about 40,000 hours in some cases. So it has a longevity. It uses a common energy source. You don't need a complicated device to turn the 12 volts off and on, and you're off running. So I might say that the large coil, which we were looking at there, I tried to use the computer programs. There's 2 of them that are available through the bookstore here. In most cases they work real well, and try to use that on the larger coil, and it didn't quite turn out the way that the program said, but that's neither here nor there. It's a good guide to what you might expect out of your coils. Okay, the 3-coil system that you see is the center one here is the one that's powering it, and you have your L1 coil and your L2 coil. You have a high voltage system, and you have 3 coils that are around it there that are tuned to the same frequency. And remember the little model that I showed you at the beginning there? Well, actually this is duplicating that sort of thing. The center coil is putting out about 30,000 volts, and so that means that each of those 3 on the outside there are doing the same thing. So you connect those up just like they were batteries or such, and you end up with about over 100,000 volts real quick like.
Are they that far away?
Say again, please.
Are they that far away?
No, they're that whole board that you see there is about 14 inches square. So, and it happens that the coils that you see there are actually about 1.5 inches in diameter and about 4 or 5 inches long. So that will give you a perspective on the size of it. This thing was made to demonstrate over unity. Since people are real skeptical about over unity, well, this is intended to really mess them up. Okay, the device, this is, most of these things are in the book, in the bookstore, and the device which you're looking at now is this particular device here. And basically what you have your 12-volt battery. You have a diode which serves to protect the laser module from a kickback. This is a high voltage laser module, and you have a capacitor that's in parallel there, and then it goes into your L1 coil and then comes back. There's a spark gap which helps control the energy level that's passing. The spacing on the spark gap there will control the energy level of the energy that's going into your L1 coil. Then, of course, number 7 is your L2 coil, and number 6A up there is Tesla's 3rd coil. And I'm going to show you something from 1893. that relates very closely to what we're doing here. These are useful circuits which I gathered up out of one of the Tesla publications, and if you notice number 1 there is showing that tuning circuit which I showed you early on, where we slide the L1 coil inside the L2 coil, and you know when you've got it tuned because you start getting sparks. Okay, we go to drawing number 2 there. If you've ever wanted to know how Tesla lit incandescent light bulbs and how he powered transformers to run motors and do other sorts of things, you have the basic circuits for doing that. This particular case, the Tesla coil is built laying on its side, and the L1 coil is in the center of it, and it moves in and out. On the, you notice the up and down thing. This is a capacitor or a bank of capacitors. Whatever energy level you need, that's the temporary storage there that gets the amount of electricity that you need in order to do the particular job that you're intending to later on. Then we go to drawing number 3 there. The coil on your right is wound in one direction. The coil on your left is wound in another direction. And the L1 coil is run in and out. The layers of the windings, if you could see them, there's layers and layers of windings here on top of each other. Instead of having an extended coil, they're wound in more compact. And the L1 coil is moved in and out there so that you get it tuned properly. And that center deal, if you put it on a timing circuit and ground it, you can get 60 cycles direct from this thing on the first go around without going through any other sort of transformer or anything else. So you can generate 60 cycle electricity direct with the Tesla coil. And number 4 is another illustration of how to light incandescent light bulbs. The trick is knowing what capacitance to use and a number of other things, but this is actually how it's done, and this was 1893. You're familiar with how Tesla was able to take light bulbs and globes and things and walk around the room and they would light up. Well, this bottom drawing, number 5, is how he did it. He put sheets of metal on the opposite ends and hooked those into his high voltage system, and was able to get enough intensity of the magnetic field so that he could walk around in a rather large space and these light bulbs would light up. Now, if you look at this drawing properly, you'll see that we have a generator there that's generating electricity that's going through a capacitor which is running an L1 coil which is powering an L2 coil which takes it to a higher level, and that L2 coil is in turn activating those two metal plates which cause the lights to go on. You can take that same circuit there and use it in a number of other ways. Okay, let's see. How's that for a spark gap? From top to bottom, it's 9 inches, to give you some idea. And this thing is made to run at in excess of 200,000 volts. And this is going to fit into something I'm going to show you next. And there's a thing called a Marx generator, which all the things which people think are not present in a Tesla coil suddenly become available. The deals here are that spark gap that we just saw. And when you take this spark gap and you put it with capacitors, just a few stages, and you're into hundreds of thousands of volts with thousands of amps. The thing's called Mark's generator. And they're used in plasma studies by universities and other sorts of organizations. Now, inside the round thing there is a real Mark's generator, and the distance across here is a little over 3 feet, so you can see that a Mark's generator is not very large, and it's very effective. And the one that's in there is multiple stages, and it goes into a couple of million volts real quick, like with about maybe 2,000 to 3,000 amps. And that creates a problem because you can't have all of that voltage and amperage at the same time, so you have to put it inside this metal contrivance, and you have to fill it with oil, and you have to pressurize it. Otherwise, you can't do it because the thing will just turn into one great big plasma ball. And once you've got it pressurized and inside oil, well, then you can contain it and take it on to your next stage. Now you can use something like this as your high voltage module to power a very large Tesla coil that goes into maybe 5 to 10 million volts real quick like, with very heavy amperage on it. Okay, I show you some other kinds of spark gaps. These are commercially available, and the ones that you're seeing in the illustration there go to about 370,000 volts. And of course, they make them for much higher voltage. If you had a ruler on there, the top one up there is about from one end to the other is probably about 6 inches long, and you have to pressurize these things, and you put a gas inside them in order to keep them from burning up. It's a sulfur compound of some sort. It's a gaseous form of sulfur, and the balls are made out of carbon, and they're made to last for a long period of time. And these things are commercially available, just like the other ones I showed you. Okay, in conventional measurement of electricity or high voltage, you have to use voltage dividers in order to get your instruments to work for you. Now, as the voltage gets higher, these voltage dividers get quite large. And in this case, in order to use conventional measuring instruments, this thing is more than 9 feet tall, and it's good for about, it's less than 1 million volts. So that means that you can measure the million volts, up to 1 million volts with your regular measuring devices by using this divider in order to bring it down to where your instruments can work with you. Now, that's not necessary at all. If you remember that for each line of electrical flux, we have a line of magnetic flux. Now, it turns out that your EMI measuring instruments or your magnetic instruments which measure magnetic flux, some of them are actually calibrated in volts. So if you have an equal amount of magnetic as well as electrical, so you can use a magnetic detector in order to read the voltage indirectly. And the way this works, you have Coulomb's or Newton's inverse square law, and the square of the distance times the remote reading will tell you what the full reading would be. So that if you're say 100 feet away or something like that, and you're getting a reading maybe 10, and so you have to square 100 and then times 10, and first thing you know, well, you're reading 1,000,000 volts, and you've got this little handheld gadget, and you didn't have to even go near the device that you were measuring the energy from. So from a safety standpoint and a cost standpoint, for about $35 you can get the a device that looks like a little handheld computer, and it reads directly in volts. So you square the distance times your remote reading, and you know what the voltage would be from the device that you're interested in. How are we doing time-wise?
We're out of time.
Out of time? Okay, can I open the floor for just a minute or two?
No.
Oh, okay, well, thank you very much.
Good morning.
Talk close.
Yeah. Where's Don Smith? Oh, there he is. All right. We're only 11 minutes off schedule here, so that's not too bad. And actually, we did need to stagger a little bit. So are you ready with the video? Okay. We're rolling. Welcome to the 1995 Extraordinary Science Conference, our morning workshop. The workshop schedules, we have a quick note. The one that says Mark Hendershot, Mr. Hendershot was not able to be here this morning, so Joseph Newman took his place. And this workshop is labeled John Picard, and he was not able to be here, so we have Don Smith in his place. And interestingly enough, Mr. Smith and Mr. Newman are talking about pretty much the same type of thing, just two different approaches, and that's a really neat thing. I first met Mr. Smith last year at the International Tesla Symposium. He was quite a hit last year, just really bent a lot of people's minds and erased a lot of preconceptions. So now we're going to have a chance to explore Don Smith's work in detail. So please, let's welcome Don Smith. Just go ahead.
Okay, I noticed one thing, the power is on the overhead. I just tried to turn it on and
Okay. I'll fiddle with that for a minute.
okay, we'll get organized here in a second.
That's interesting.
Okay, we better hold it till we get our electricity going here.
I think they're going after another one. Okay, yeah, go ahead. They're running after another one. I'll make sure they are.
Okay, well, until this thing really gets to going, where I can put some things on for you, some overheads. I'm going to work largely from overheads, and the floor.
Talk into the microphone, and you can take that off the stand too.
Okay, I'm going to work largely from overheads, and the floor is.
There you go.
Okay. I'm going to work largely from overheads, and the floor is going to be more or less open to questions as we go along. And then at one point along the way, we'll stop and we'll look at some of the devices, overhead devices. How many of you were here last year, so I'll know what not to repeat? It looks like I could probably repeat a number of things that we talked about last year. There's a book on this which is available out the bookstore, and I have a few copies maybe myself, and that sort of thing. I'm going to show you what the front cover looks like on it so you know what to look for. It has, in event you don't get all your notes on it, it will have almost everything that we talk about here in it. If it doesn't, well, it's got my address and phone number in the front of it, and I get lots of phone calls on these things. Last year, after I went home, by the time I got there, there were several hundred phone calls on the answering machine, and I got from 20, 40 to, I guess the highest day, maybe 80 phone calls from people from all over the world, and sometimes in the wee hours of the morning. And the book that we're talking about, they have some of them in the library, and I have a few copies myself in case you miss out on the ones over there. I noticed they didn't appear to have very many of them, so they must have another box somewhere. Okay, this is going to get interesting because I'm probably going to have to come down closer to the overhead so I can start putting things in. And I don't want to get in front of you, so let's see if I can get over out of the way here. Okay, well, that's the front page on the book that we were talking about, and it's growing. There's going to be about 400 pages in the book, and it's going to look real nice when it gets finished. I noticed that Joe Newman over there has already got his book finished pretty much. It looks real impressive. And he's doing some of the things which I'm involved in. I notice he's using the 200 kV capacitor there, which is one of the tricks to getting useful energy out of one of these devices. Basically, you have to have some way of storing the energy in order for it to become useful. And there's several ways of going about making it useful. One would be using a diode bridge. And the problem there is that most of the diodes that are available aren't high enough frequency or high enough voltage or amperage. You can get diodes that are above 2,000 amps, but generally speaking, the frequency rating on them eliminates the use of them. There's an interesting way around that, however, because the equivalent circuit of a diode is basically a capacitor with a resistor shunt on it across the two poles of the capacitor. And when that's in, yes?
Maybe we can just use the old vacuum tube diodes. They seem to be...
Yeah, well, you can use those. They'll get you into some higher frequencies and maybe even some higher voltage.
Higher amperage as well.
Yeah, and how to identify a diode that works at high voltage, the length of the diode has to do with the voltage and the diameter has to do with the amperage that it will stand. Generally speaking. That's correct. Okay, I'm going to start putting these slides on for you. I did a thing here last year, and some of the stuff that we're going to be doing will be coming from that. This is not. This is give you a little bit of a general summary as to what to expect from this thing and what's the ongoing situation is. There were numerous people who approached me wanting rights to manufacture the thing commercially after I was here last year, and a lot of them turned out to be promoters, and a lot of them turned out that they didn't get along with each other or their money source or me either, and I had to run some of them off. And for the last 6 months, I've been trying to get rid of one group, and I did get rid of them. I got along real fine with the funding source, but I didn't get along well with the guys that had gotten in between. And the funding source basically is a part of the World Bank and some of the other people, and it involves the rural electrification of India, Pakistan, and China. And I'm their consultant on how to do it, sort of thing. So then the funds are there, the contracts have been let, and everything is in place. So within the next year, we'll see some very interesting developments as far as this technology goes. Most people think that lots of volts and no amps. And that's the thing that try to get you with every time. However, volts are basically the water that's behind the dam. Until you poke a hole in the dam, you don't get any flow rate or amperage and that sort of thing. So whatever your voltage is whatever your potential is, and how you go about letting that thing through the dam is what's going to give you your useful energy. And in this case, the useful energy is accumulated in capacitor banks, and a megajoule range is not unusual at all. And I'm going to show you some things after a while that relate to this that are in place, and you can actually buy them off the shelf, so to speak. And they work for rail guns, plasma studies, and a whole slew of things. Most of the universities have these capacitor banks. And with that, we'll move on to something else. One thing that we need to take note of is that you're always faced in this type of thing with whether something is unity or over unity or what happens in that case. Now, basically, anytime something is nonlinear, it has potential for over unity. So if we go back to the time of Galileo, and we find that he had the first two laws of motion in place, And along later came a fellow by the name of Isaac Newton, a farm boy from studying mathematics in Cambridge University, and he added the third law and also changed it from the laws of motion to the conservation of energy laws. And of course he got knighted for that, among some other things, and became one of the professors of physics at Cambridge University. But his basic background, his whole family were just tradespeople or farm people, and as a student at Cambridge, he was not particularly noteworthy in any respect. And one day he got in a fight with one of the other students, and something about that fight changed his whole chemistry, and after that he became one of the best students in Cambridge, which if you go back to the 1600s, Cambridge is probably like one of the little agricultural colleges out here in the backwoods somewhere. So it wasn't the Cambridge that we know about today. And sometime later, a fellow that was a bookkeeping clerk in the patent office by the name of Albert decided to paraphrase the whole thing into energy equal mass times velocity squared, and of course he got the Nobel Prize for that. And so if you fellows want to do something great, you've got some good company there. Anyhow, once we get into the laws of motion and into the EMC square thing, it's real easy to convert that over to what we want to do, because basically in the energy business, you've got magnetic and you've got electrical energy. They're both the same coin, just different sides of it, and you don't have one without the other. If you've got electricity, you've got magnetic energy, and if you've got magnetic energy, you've got electricity. So that's going to come back in a little bit, and we're going to find out how to measure the large amounts of electricity that we have very safely. What that means basically is that your electrostatic voltmeters and other kinds of things that measure magnetic flux can be used due to Coulomb's inverse square law. It was Newton's before it was Coulomb's inverse square law, which means basically you take the remote reading and the square of the distance times the remote reading, and you've got a direct reading on the magnetic flux, which converts directly into electrical flux. So you haven't had to poke your finger into a 2 million volt device in order to measure it. If you try to measure it with the conventional systems, I'll show you some after a while, you'll have a resistor stacked as high as this ceiling here and then some, in order to divide the voltage down to where you can measure it with your instruments. And that gets to be very complicated. It's also very dangerous. So it's much easier to use the magnetic flux, which is the actual other side of the coin, but it's not dangerous like the electrical flux. Okay. Okay, electrons provide us with a lot of different kinds of energy. We see that we have a source of electricity, we have a source of magnetic energy, we also have spin. When the electron spins, it gives off energy. It also gives off light. When two electrons get too close together, they immediately push apart, and when that happens, you get a flash of light. That's where your daylight comes from. It's the electrons that are coming in from the solar plasma that impact the Earth's on the side of the Earth that's spinning into the solar plasma, and when they get too close together, you get flashes of light, and that's where your daylight comes from. If you get outside the Earth's field, you just have dark. It's very black out there, and you see stars off in the distance, and they're just pinpoints of light. The sun itself just looks like another star. So to give you some idea as to where the energy is coming from and what happens then. Okay, the establishment has a problem with this term unity. Basically, what happens in unity is that ambient or background is what you're really seeing most of the time. And in the case of sitting in this room here or anywhere in the general area here, the voltage, background voltage is several 100,000 volts, but you're not aware of it because it's the same all around you. So if you want useful energy, basically what you have to do, you have to get above ambient or below ambient. The water has to try to go back down the hill, so to speak, or things try to equalize, and otherwise you have no useful energy. So the fact that you have all this electrical energy around you, which can be measured fairly easy, doesn't really mean anything because it's not useful to you. And apparently it's not all that harmful either. Okay, we'll go from that. Whenever we start doing our conversion from EMC squared to our formula, which we're going to use, remember now that half the energy is magnetic and half of it is electrical. So we're going to put, it's crooked. Okay. Half the energy is electrical and half is magnetic. So we're going to have to multiply our formula by 0.5, which is half, in order to get, say, the electrical energy, which is what we're actually looking for. So whenever we're going to let, in our case, energy, we're going to let it equal joules, which happens to be a universally convertible unit. And we're going to say that joules equal mass. In our case, mass is going to be coulombs or electrons or whatever you want to call it. And the way we're going to collect those things is in a capacitor. So our formula is going to read joules equal 0.5 times capacitance times, in our case, velocity is going to be potential or voltage. And those things convert over relatively easy. And the next thing we have to do in order to ascertain how much energy is there is to take the number of cycles per second. So we multiply what we have just got by cycles per second. In capacitance, we're using our farads. So we've got something like 0.3 or 4 zeros, and then we've got a number. And then we're multiplying that times the voltage, which say is 100,000 volts or more, and that sort of thing. And that's going to move the decimal point over some in your favor. And then that doesn't really amount to a whole lot of electrical energy at that point. But whenever you start multiplying the number of cycles per second times that, then all of a sudden you've got an awful lot of energy. And basically what happens at that point, you pump it on into a set of capacitors or a capacitor bank, and that capacitor bank takes it on from there. And one of the slides I'm going to show you in a little while shows you that in 1893 that's exactly what Tesla was doing. It shows the circuits for running motors and electric lights and that sort of thing. So he was actually doing the same thing then. So it's not anything new. It's how you go about doing it and the type of capacitors and a few other things that you use. Now, where you get into trouble on this sort of thing is the fact that you think a resistor is a resistor. Well, it doesn't really turn out that way, because most of the resistors are better capacitors, or they have more coulombs and more henries than the actual things that you want to get those out of. So you have to have resistors that are non-inductive and non-capacitive, and those are a little bit hard to come by. They exist, and if you go into a electronics store and try to buy that sort of thing, you're going to get very interesting reaction, because they've been in the business for about 50 years and they don't have never picked up a resistor and measured the LC factor on it, huh?
Yeah, this problem presents itself very clearly in radio,
Uh-huh.
where you try and dump a lot of power out of a transmitter into a load. If you use a large, say, 50 ohm wire wound resistor,
Uh-huh.
the inductance of that wire wound resistor will present a different impedance to the...
Yeah, it messes up your impedance, and your device doesn't work, and a whole slew of other things. Now, since last year, there have been hundreds of people that have tried to duplicate what I did, and there's about 12, I guess, out of several hundred that were successful. And the main reason most of them failed was the impedance problem, because when they started putting capacitors and resistors and, you know, various other things in there which control the timing circuit so that the different coils could talk to each other, well, basically they blew themselves out of the water. And none of them, or very few of them, ever bothered to check to see if there was something there other than resistance or capacitance or whatever, or even in your L1 and your L2 coils. For example, some of the L2 coils I have like 300 or 400 microfarads, you know, and that's not...
The coil is very poor then.
Yeah, well, you can change that very quickly. Basically, what that tells you is that instead of having 400,000 cycles a second, you got 400 cycles per second, which actually that's kind of interesting, because that's down in the range where you can start running electric motors and such. So the potential exists there for going directly to the motors instead of having to go through several stages to get to them. You know, because a lot of motors run at 400 cycles per second. The ones that are used in airplanes and the controls of airplanes and a number of other places, and they have a lot of torque on them. They're small, they have a lot of torque, and a lot of horsepower for the size.
Yeah, because the inductance increases as the square of the frequency.
Yeah, well, see, whenever we talk about ambient and that sort of thing, we get into a situation where as the frequency increases, the magnetic lines increase, and it's those magnetic lines of force that disturb the electrons, which cause more electricity to become available to you. And that's basically what's happening on your L2 coil. As you start from the bottom of the L2 coil and go towards the top of it, each winding there has capacitance and other types of things, and those things start squaring as you go up towards the top end of the L2 coil, and the net result is that you have a tremendous magnetic flux field going on up at the top of that coil there, and so that also presents you with some real interesting possibilities, because that's the end that you really want to get your flux off of in order to go ahead to your next stage. And a small coil, I'll give you a for instance on it. Say that that L2 coil has 100,000 volts potential, okay, and it's cycling, say, at well, it's normally going to be above 20,000 cycles per second. So in order to ascertain how much energy you've got available to you, you have to multiply it by the number of cycles per second. So you can see that with 100,000 volts output on a Tesla coil, that you've got way into the high megawatts or megajoules. And if you've got a way of containing that energy so that you can get it onto the next stage properly, which that's your capacitor banks. And a real nice capacitor bank for a megajoule production deal, they're available, I want to say, off the shelf. That's not really true, because there's no two of them that are ever alike. But I'm going to show you some in a little bit, and you'll see what the size of them would be. Some of them are about the size of that podium there if you double the height on it, and that would be approximately 1 megajoule. So, and it consists of numerous banks of capacitors that are in the, say, the 200,000 volt range and that sort of thing. And you might say, well, how do you get capacitors in that range? Technically, it's not as difficult as you might think. There's your dielectric or your separation deal that separates the plates there. There are several types of things. Kapton is one of them. It has about 7,000 to 8,000 volts per mil. So several mils on that, you're beginning to move up into the voltage, and by the time you get up to, say, a 1/16 of an inch or something like that, well, you've got real high voltage. Yeah.
What was the name of that material?
Kapton. It looks like mylar, and it's kind of amber color, and Dow Chemical Company makes it, and a lot of people sell it. It's not always used for capacitors. It's used for a lot of other things.
For heat sinks and so forth.
Yeah, you can put printed circuits on it and things like that, and you can build a radio device that you can roll up inside something the size of a pencil that's equal to a large color television or something like that. You print your solid state devices right onto the circuit, and then on top of that you put say another sheet of it, and then you press it so that they seal against each other, and the net result is the whole circuit is inside this very high voltage dielectric, which doesn't really, all it does is just protect the device. Okay, let's see what else we've got here. In transfer of energy, you have what's called volt amperes reactive, and what I'm showing here is the conventional power triangle in energy transfer, and number C on there is considered to be wattless energy or useless energy or whatever, and that's your volt amperes reactive part of it. Your A part there would be volts times amps, which is electricity that's in the wall that until you ground it by closing the switch is not useful, and at the time you ground it or run it through a device to an earth ground or whatever, then you've got number B there. So anyhow, in this power triangle, you can take a small power unit and you can power a much larger power unit. For example, an example of that might be an atomic bomb, because you use a small bomb to set off a larger bomb, which in turn sets off the atomic bomb. And in this case here, you can use a small power system, and you can pump a much larger power system. And doing that, you really don't have to pump it all that much, because like I mentioned a while ago, at 100,000 volts, you're into the megajoules range already. And 100,000 volts is relatively easy to obtain using a Tesla coil. Even a small one can do that. And the large ones, you probably have too much energy, and it's self-defeating after you get past a certain point, because even if you were able to contain it, the containment problems would be so great that you'd be better off to try to do it at a lower level, because you can use multiples of these units instead of one gigantic one. And if you need megajoules, for example, one of these units that has about 100,000 volts output with the proper capacitor bank and that sort of thing can equal Hoover Dam, which is about 500 megajoules. So you've got something that will sit on a coffee table that will equal Hoover Dam. or it's larger. It's as large as maybe 2 or 3 atomic energy plants, and yet you're actually using a small amount of energy in order to activate a larger system, which in turn gives you off your potential, and the potential is captured in capacitor banks and that sort of thing, and at that point, well, then you can process it further. Okay, I'm going to show you the formula that relates to what we're talking about. And then we're going to run some case histories and let you see what happens from there. Okay, if we have any questions as we go along here, be sure to let me know. We're going to stop after a while anyhow and take questions. And we've got enough material here to go for several days, so we're not about to run out of things to talk about. So as you see, joules is a universally usable term for energy. A brewmaster, English brewmaster, in his brewery had all kinds of different kinds of machinery, including electric and steam and other types of things. So he came up with a unit which was convertible into other systems. Basically, a joule is a watt second. It's a volt times 1 amp times 1 second. And that's not a lot, but when you get into millions of them, it becomes a lot real fast. So we're going to be seeing this same formula over and over again as we go through the documents. Okay, we're going to skip over onto something else and then come back to that formula. In the law of squares, where you see this a lot is in nature. For example, in the case of a human being, you take one cell and it divides and it becomes 2 cells, and then 2 become 4 and 4 becomes 16, and by the time you've squared that thing several times, well, you're into a million. So this same thing applies out into the universe and a lot of other areas that we know about. In our case, the electronic flux that we were talking about is you move from one unit of electronic flux to a larger unit of electronic flux. These things are squaring, and as the flux squares, the number of electrons that are being disturbed is squared, and the net result is that you end up with a lot of energy that you did not have there previously. So the people that have a problem with over unity, basically everything that is useful is above ambient, so everything that is useful is over unity. And whenever you start squaring it again, the laws of nature dictate, not only in living creatures but in the field of electricity and other areas, we see that it doesn't take very many of these leaps until you have a very large amount of electricity looking at you.
Is there any particular coupling distance?
As to the magnetic force, it's governed by the law of the squares again, which means the square of the distance times the point that you're reading.
The inverse square law.
Yeah, so if you move your things away from it, now you get around that to a certain extent, and I'm going to show you a device after a little bit that works like a radio station, where if you have one coil running at a certain level and you have other coils in the general area, if they're capable of responding to that frequency, that they will duplicate exactly what's going on in that first coil. So you can have one coil that's running at a certain energy level, and you can have dozens of other coils sitting around it, and they may be different distances, but the fact that they're being stimulated by this central source, they start reacting just like they were that original source. Okay, we're back to our formula again there, and we're actually substituting some things into it. So you haven't added the 0.5 yet. You'll see that come in just a little bit. All this information is in that booklet that in the booklet that I mentioned earlier. And there's also some schematics and things which all along I've tried to get people to build their own device. And okay, well here's where our point 0.5 comes in. Okay. Can you read that okay? Okay, this table could be a little larger. Okay, well, you're going to see the same formula, but it's going to be with some things added to it. I'm beginning to show you what happens, and then I'm going to take a real big jump just momentarily. So you can see that I had mentioned earlier using this, I'm trying to demonstrate what happens with the 60 cycle system and why the amount of energy that comes out of it is not as high as it might be otherwise. That number of cycles per second is what you want to watch for, because it's building or ratcheting up the power level for you. So we don't see a lot of energy on this thing, but we're going to very shortly and see what happens. The same formula is going to turn up again. Okay, can you see it this time? And you'll notice that what happens whenever you have 100,000 volts of electricity, which I had mentioned earlier, and when you start multiplying it by the cycles per second and the other factors that enter into there, you can use much larger capacitors than I've used there. I've used relatively small capacitance, and you can switch higher capacitance in there, but your amperage is going to burn up your coil almost immediately. The moment you start raising that capacitance, your amperage is going up tremendously, and you may end up with 4,000 or 5,000 amps almost immediately. And it's obvious that the equipment that you have, including your capacitors, probably couldn't handle it. So basically what you would have hot spots on your coils, which would end up melting off the protective coating and maybe even melting your coil. And the capacitors would probably fail because the dielectrics and other things would be heated up so much inside that you couldn't build a capacitor which would function with that kind of amperage. So how you get around that, you have banks of capacitors in parallel, and none of them individually are loaded to the extent which would cause failure, but by the same token, all added together, you end up with a product that's very high, and you end up with an awful lot of amps and an awful lot of volts. And where you see this in practice, the rail guns, which the military works with, is one case in point. All the universities have high energy departments, and most of them have Marx generators and other types of things which produce very high amounts of energy from a relatively small device. And I'm going to show you some of those after a while, and you'll see some multi-megajoule devices that are not very large at all. Okay, how long, where are we right now time-wise? Have we got an hour yet or not?
Yeah, 10 minutes.
About 10 minutes? Okay, we'll start looking at some other things then. Let me know when we get, well actually we're supposed to take a break at 10 minutes till the hour. For about a 10-minute break, and then we'll come back and we'll start on some actual devices and other things that go with those.
Well, there are things you can do, because sometimes you can do them out, but
Okay, let's see if we can get started. We've got more material to see and look at and that sort of thing than you can imagine. And most of you have been wondering what these things look like when you actually build your own. I'm going to show you some right now. Okay, those did not come out as clear as I would have liked for them to. You're looking at one there that's in the megajoule range. Basically, what you're seeing is a 12-inch PVC pipe that's been cut in a piece that's about, top piece is 16 inches or so long. The bottom piece is about 16 inches or so long. The larger round thing that you see there is a Rubbermaid drum dolly, which I took the rollers off of. And it happened to be 25 inches in diameter, which was in the acceptable range for the L1 coil. And what you're looking at down below, you're seeing this is an automobile ignition coil from a 1968 Pontiac. It's brand new, however, the coil is. And I've built a timing device which is built onto this particular deal here. It consists basically of an electrolytic capacitor that's I think it's 4,700 microfarads, and it's not very large. It came from Radio Shack, and I think it was maybe about $2 and something. And there's a shunt across the two arms of the resistor, two arms of the capacitor with a resistor on it. And it doesn't take a very large resistor because your basic cycles per second there are going to be the multiplication of the resistance times the capacitance that you have. And that works backwards, so that if you had, say, 10,000 microfarads and you had, say, 100 ohms, that's moving the decimal point in such a way that you'd actually multiply 100 times the capacitance there, and you'd see the number of cycles per second. Now in this particular case here, since we're using an automobile ignition coil, we know that the RPM on an automobile is, when it's running at normal speed, is maybe 2,000 or more RPM, and you've got 8 cylinders there, so you would think that the times off and on of that particular automobile ignition coil at its normal frequency would be about, say, the 2,000 or more times of your capacitance. Let's see. So your cycles per second there is going to end up being like, say, 14,000 or 16,000 or something like that, which is not very many cycles per second. But it turns out that that's enough to make a dent in things, and if you multiply that times some of your other factors, well, you end up with a lot of energy out of this particular coil. So this is one that you can build yourself real easy. Yes?
How much energy are you getting out of that?
Well, this particular one, there's 2 computer programs which are available normally, and then I have a couple others which aren't normally available. And I used every one of them and ran the thing, and I came out with very, very different answers from each one of them. This one was supposed to have come out 400,000 volts at a fairly high cycles per second sort of thing. And whenever I got it built, it turned out that the capacitance by the large diameter and the capacitance between those wires, it came out with a natural frequency of 400 cycles per second, which a while ago I was mentioning that it's possible to build these coils so that they will run down in the range where you can get electric motors that are set for that particular cycles per second. Yes?
What kind of wire are you using out there?
Well, what you have to watch out for is the fact the voltage difference between 2 wires. So if there's 750 volts different protection on one wire there, between the 2 wires you would have 1500 volts possibility that you could play with, so that you could have a differential of voltage going as you go up of 1500 volts, and you'd probably want to stay at about 1000, which would give you a 500 volt safety factor. In this case, there's 130 turns on that thing, so it'd be 130 times your 1000, say, if that's what you put on each turn of your L1 coil, which would be this one. It has 3 turns.
Your L1 coil's got 3 turns?
Yeah, this one has 3 turns of number 8 wire. Yeah.
And the L2 coil has how many turns?
The L2 coil has 130 turns on it, and it's number number 14, I believe.
Number 14?
It has it's multi-strand wire, because if you use the solid wire, it's very difficult to control and make it look nice. The solid wire goes its own way. It's very difficult to make it. Sir?
Litz type wire?
What type of wire? Yeah, it's not truly Litz type wire, because to be Litz type wire, each individual strand, when there are many strands, has to be individually wrapped with a little piece of cloth or something to be a true Litz wire. But it would qualify as a Litz wire under the terms that we would use maybe today.
Like grounding cable on a lightning rod, you know how...
Yeah, basically what happens is that these multi-strand wires are made for DC, generally speaking, which any sort of resistance knocks the DC down real quick like. So you're using a DC type wire, but you're using it with AC.
What are you using there on your secondary?
On the set, it's a multi-stranded wire.
Where do you get that wire?
I got that at one of the electronic supply houses, but I noticed that Ace Hardware and some of the lumber supply places have very similar wire.
What gauge is it?
It's number 14.
What voltages were developed in the secondary build?
On the secondary, that depends on how much you put in from the input source and what kind of resistance you put between that and the other thing. Now, there's some diodes and other things that are in the circuit there that control what's going in. So the output on this thing was, even after you go through all the commotion here and that sort of thing, is like maybe 70, 80,000 volts. Uh-huh.
What's on the top of that picture up there? What do you have on top of that little terminal block, that little square?
Okay, kind of direct me a little bit. Here's the detail on this thing right here. So, well, the spark plug goes to the earth grounding. That is, you've already passed through all the circuits, and your timing is all set and that sort of thing. And as a control on the load that's going to be built up, your potential that's built up, this thing, it goes to an earth grounding. See, if you notice on the output coil here from it, there's only one wire coming out. Okay, somehow you have to get back to your negative pole on your battery or a ground plane or something like that. So in this case here, there's another cord that hooks onto this, and it goes to an earth grounding, which there's an earth grounding that comes off of one corner of that high voltage coil there.
It's the small orange and yellow mechanism in a U-shape right behind the spark plug.
I couldn't understand.
On the terminal block, what is the small orange and yellow mechanism?
A small orange and yellow. Actually, what I've done here, you can't really see it, but I've got a circuit that's going along here with a capacitor on it and a resistor, and I folded it back. Instead of having a series thing looking at you that would go out like this, I've gone down, skipping the contacts there, and then I've come back to a certain point. So I've got a resistor and a capacitor in that deal. It turns out the capacitor is about this long and the resistor is about that long, so the net result is I loop back, and that orange thing you see there is my where I had a blank space that I had to bridge in order to get the circuit closed, and that's what that orange thing is. There's nothing magic about it. Yes?
I must have missed what that little square thing was back there. It looks like it's got writing on it.
I have trouble hearing you.
It looks like a large capacitor.
Is that a capacitor, that white?
Yeah, you're looking at a 10,000 volt capacitor there. It's reconstituted mica, and it's building up. That's actually what's it's working between the blue one here is the negative lead coming back from the L2 coil. The one that's white here is your positive lead going out. So between those two, in relation to your other things, you've got this 10,000 volt reconstituted mica capacitor, which how that happens, they take mica and they break it up in little bitty pieces, and they mix it into a glass ribbon type deal, and that becomes your dielectric in this particular case, and they go to very high voltages. I'm going to show you some in a little bit that go to over 250,000 volts.
Yeah, this one here was what farads it?
It's 0.01 microfarad at 10,000 volts, and I think it cost about $200. The mica capacitors are a little bit hard to find, and no one likes to admit that they have them. And even if you find somebody that has them, they'll be looking right at it, and they'll be looking at you, and you'll be asking them if you tell them what you want to buy, and they don't have it. In this particular case here, this one came up from New Jersey, and I had the listing on it, and I knew what they had. I called them, and they told me that they had them on the shelf and that they could send me one. I said, well, fine, I can use it as soon as possible. And they weren't doing anything. They were not busy at all. And they said it'd take them about 6 weeks they could reach over and touch it. And it'd take them 6 weeks to reach over and touch it and put it in an envelope and UPS it to me. So anyhow, we went round and around, and I got it down to where it took me it was a week getting to me after I located it. Yes?
Does this unit, do you have any load on this device at all?
Well, before you can put a load on them, you have to put it into a capacitor bank and get your thing built up so that you have something to put a load against. If you try to put a load directly onto it, it's going to detune it, and you'll end up with nothing. Okay? We have some more. Okay, that's that particular device. Okay, here's one that I'm going to show you the schematic on in a little bit. The top one there with the yellow deal on it, actually your L this is going to be your L1, this is going to be your L2, and this is going to be an L3. You remember I said that the lines of magnetic flux on the distal end or the busy end of the Tesla coil are very large in number. Okay, well basically what's happening there is that this is the offtake that goes into the diode bridge that you see there. That diode bridge is built on the underside of a plastic case. One half of that plastic case, it's a little box that you build electronic projects in. And coming out, what you're interested in here, this is going to be your plus DC, and this is going to be your minus DC. These are your two AC things going into the diode bridge. Okay, at this point, this particular one is set up so that you get 60 cycles at usable level where you can just plug directly into it and you're off running. And it's intended to go directly to without the capacitors and other things, and it works fairly well, but it would work a lot better if there was a nice capacitor bridge in there somewhere before you get to the area where you're using it. Now, from this you go from your plus DC, you come over to the center deal here where the jumper is, and that enters into this inverter circuit, which is the device that you see here is what you get down at Radio Shack that you plug into your 12-volt deal for running things from your automobile. It's 60 cycles at 120 volts. And the resistors there and those transistors you see, those happen to be very high voltage and amperage transistors. And you can see that they're on a heat shield type deal, which helps control them. And if you run it for any period of time, of course, it would probably overheat. So in order to get a practical unit which you can use over a long period of time, there's still some engineering to be done there, but the basic idea works. Yes?
What are the small knob-like devices on the lower picture?
Okay, down here. Okay, this is a system I mentioned earlier that you could have individual coils sitting around that were tuned to a coil that was active, and that they will copy exactly what the other one is doing. Okay, well in this particular case here, this is the one that the Tesla coil with your L1 and your L2, and it's the one that's hooked into the system, and it's the one that's active. Okay, the other three that you see there are simply tuned to that center L2 coil there, and they do exactly what the center one does. If the center one has like 30,000 volts on it, well, the other three will develop independently 30,000 volts, and they do not draw down on the power from the center one. It's the electrons are moving around, and the natural frequency of those coils, actually they have variable microcapacitors, high voltage microcapacitors on them, and they have also a variable resistor on it, so you can tune them individually. And how you know when they're tuned or when they're actually functioning, there's a little neon light that you get that's got one leg with a resistor, about a 47,000 volt resistor on it, and on one leg of the wire that's on this neon bulb, and then there's another leg there that just sort of sticks out like an antenna, and when this thing is functioning properly, well, that bulb lights up. So you know immediately when it...
resistor in series with a neon bulb?
Can you use 1,000 ohm?
You said 47,000?
That I measured one of them, and that's what it came out. They didn't specify on the package.
That's pretty well standard for, I think, a 240 volt neon indicator.
Yeah, well, anyhow, the bulb lights up very brightly, and you have no trouble at all. It takes 70 watts, I think, to light the thing, something like that. I'm going to show you a thing in a little bit where you can order. As a matter of fact, it's the next slide. There's a company in Waldenboro, Maine, who manufactures a device which actually illustrates everything that we're talking about here with all the formulas and everything else, so that if you're interested in studying it, you can get this kit, and it's got the price on it, I think, there, and give you some ideas. It's not very large. It's a little bakelite tube that's about 2 inches or so in diameter, and that's what you've got here. And you've got a tuner deal on one of them, and the other one is already tuned. You've got a 1.5 volt battery, and the output it lights this neon 70 watt neon bulb. So if you have trouble, are uncomfortable with what's going on there, well, this actually illustrates your over unity. As a matter of fact, it was one of the first things that I knew about. I'm a geologist, actually, and about 10 years ago, when the petroleum industry went sideways, friends of mine tried to get me to assist in the high school science department in a large high school that was close by, and I did. And of course, I ended up teaching physics and chemistry and a bunch of other things. And the students in our particular neighborhood, we live in an upper white-collar neighborhood, and most of the parents are all advanced degrees from the large eastern universities and that sort of thing. So you've got a bunch of kids that are pretty sharp, and if you don't defend yourself, well, you're in trouble real quick like. So anyhow, I was very successful at it, much more so than the regular teachers, and this was one of the devices that I used to teach radio characteristics in physics. And that was the first time that I was aware of the fact that this over unity type thing was a possibility. And that was more than 7 years ago. And I was very much into it, far advanced before I knew about Tesla, and but I didn't really remember much about him. And people started telling me, well, that's the sort of thing that Tesla does. So I started getting every book that I could find on the subject, and we have a neighborhood library that's on a computer system that's hooked into all the libraries across the United States, and it didn't take very long to end up with books from the City Library of New York, Harvard University, Caltech, and just about everywhere else. And one of the books I got was purchased by Harvard University back in 1937, and I was the third person to check it out, so you can see that the subject was not all that popular, apparently, and I didn't quite know what to think whenever I saw that, there had been only 2 people that had checked this book out, and it was a very important book, and it was from a major university. So it seems like in this particular group here, we have a hotbed of people that are interested in that sort of thing, but people in general, apparently are not all that interested in it. Yes?
Yes, I still have a question about that other slide, if this is a good time, or if I...
Which one? You want to see the circuit?
The circuit,
Yeah.
the slide you have prior to this,
Uh-huh.
picture that small unit.
Uh-huh.
that you had there.
Yeah, I've got it. It's coming up. It's in the stack here of things which I'm going to be showing
Go
you.
back to it.
Yeah, we're coming back to it. As a matter of fact, we have so many things to look at that it will kind of boggle your mind.
What frequency range is that device?
That device, if you look closely at this one, this is running down in the AM radio range. You can tell that by the size of the coils and the number of turns. Just looking at it, you can tell that it's going to be in the AM radio range. And I think I got your phone number on there, didn't I? And an address and everything. I tried to... I took this out of a science catalog and Xeroxed it, and then cut the pieces up and pasted them on another piece of paper in order to get this slide for you. it's one of the major scientific supply houses that normally has it, but this particular one is on the front sheet of the instruction thing, which is about 9 pages long, front and back, that comes with it. And this is the bottom part there. The top part is out of the catalog.
What's on the very left end of the board?
Flashlight cell?
RCA.
That's a 1.5 volt flashlight battery.
Says RCA.
So-
When you look at it sideways.
Well, if you notice what that 1.5 volts is doing, you'll notice immediately there's something there that doesn't match up with what you would expect to happen.
Well, there has to be some sort of circuit interrupter, a key or something else that goes with it.
Well, there's a capacitor in there. There's a capacitor that's,
See the tuning
yeah, it's a small capacitor. Well, actually, you can see there's a butterfly capacitor there that's in the like 250 microfarads or something like that. Or picofarads, it's probably picofarads, 250 picofarads, which would get you into the AM radio frequency with that particular coil winding.
Right. Little tank circuit.
Yeah, it's a tuned tank circuit, and the other one, the second one there, is on a block of wood. You can move it around the room. You know, we were talking a while ago about the coils being able to be somewhere else, and they work just fine. Okay, if you decide to build yourself a Tesla coil, one nice way to do that is to get one of these little push carts like Rubbermaid makes there, especially this one would be very nice. And I think this even has the prices on it if you want to see how much they cost. If you want to go first class, well, that's one way to do it. Of course, the insulation of the plastic push cart there is very helpful to you. And you can build a little bit larger platform on the top of it, or just use it the way it is. It's okay to move this? Okay, let's see here. We're going to come back to that schematic in a little bit. If we don't, well, be sure to let me know. And if we get close to our second hour ending here, also let me know, and we'll take a 10-minute break. If you want to see what was going on in 1893, here's some circuits here which are not at all different than what they would be today, except that you have better capacitors and other things. You notice there's not very many parts there, and there's a tuning is built into these devices to a large extent. You notice on this particular one here, this is your L1 right here, and this is your L2 here, and you're actually tuning this thing by pushing the L1 backwards and forwards in there till it actually matches up with the tuning deal, and you've eliminated the possibility of having to put capacitors and a number of other things, because the capacitance is already built into the wire that's part of the coils. So you've simplified, and you've taken out some stages there which would create a problem for you unless you just happen to have a lot of nice test instruments, and you're able to match up your capacitors, resistors, and the characteristics of the particular coils, so that you end up getting what you want. Okay, that's your number one drawing. Number two drawing there is showing the capacitors combined with the output thing, and the top one there is set up so that you can run a conventional transformer directly. And if the frequency of the coil is something other than what you want, on that number 2, just slightly above where the number 2 thing is there, you can put a resistor or a capacitor in parallel across that particular coil there, and you can bring the frequency down to where it will match your transformer. Okay, the bottom number 2 there is showing how to light light bulbs, conventional incandescent light bulbs. How's that? Have you ever wondered how to light conventional light bulbs? You can light fluorescent bulbs fairly easy. You don't even have to plug them in. You can just hold them in the general area where this thing is activated, and their fluorescent bulbs will light up. But light incandescent bulbs gets to be a real problem. And the thing there that makes that possible is the capacitor, and we're going to substitute that capacitor with a capacitor bank in a little bit that has in the megajoule ranges. And at that point, we're off running, and we can produce any amount of energy, useful energy that you can imagine.
What's he doing on figure 2 up there at the top?
The top figure 2?
Between the left coil and the right coil, there's something in between there. What's that?
The tall thing that's kind of in between there, that's a capacitor or a capacitor bank. See, these are actually Tesla's drawings. You're looking at something that Tesla himself actually drew.
What is the spark gap for?
The spark gap is actually control the level of energy that's passing through there. You can do it without the spark gap. I'm going to show you some fancy spark gaps in a little bit that can be used in real high commercial type spark gaps. Okay, come down to number 3 there. That is a device which I built a model of and demonstrated last year. And what it amounts to is that you've got a transformer, you've got your L1 coil, and you've got 2 L2 coils there, and the base of both L2 coils are hooked together, and a ground actually comes off of this thing, and you put a timing device on that ground there so that these 2 coils are activated for 60 cycles. And one of them is wound reverse winding, and this basically what it does on part of the cycle, when you got your conventional cycling doing this sort of thing, well, one of these coils takes it up like that, and then the other takes over and takes it down like that. So you get your conventional sine wave deal at 60 cycles directly from a Tesla coil from base 1. And where you go to from there, depending on the amps that you want to be bothered with, you use a very heavy wire, maybe a size 4 or something like that, or maybe even size 2 or 0 or something like that, and you make these things quite large and heavy, and then you make your L1 coil out of rather heavy stuff also. And the net result is when you pump the capacitor bank with this, you've got so many amps that you have trouble controlling them.
This operates at 60 cycles per second with no iron?
Well, remember now I said that on the grounding wire, that center one that's in the middle there, it has to go to an earth ground, and you have to put a timing deal on that earth ground, which will cause the 2 coils that you see there to actually, you have to do it at 120 cycles because 60 cycles up and 60 down, and the net result is that adds up to 120 cycles, and you come out with the actual full cycle is 60 cycles.
Question.
Yeah.
The device shown in 3, that's a 2-dimensional drawing. What is the upper half of that? Is that a toroid? Are those toroid?
Well, those are wound somewhat. You see the layers of wire going across them. It's not a true toroid. exactly how to describe it. It's layers of windings on top of layers of winding. On a true toroid, you've got it.
Right, but I noticed that he's got the representation of coil both above and below.
Yeah, well, what you've done, you've sliced through the center of it. You're looking at it like a piece of cake, looking at inside of a cake or something.
So that is actually a two-part coil.
Yeah, it's round coming out this way, and it's round going back that way, and it's got a round L1 that's being pushed in and out of the center there, which is tuning it in the same time.
A C-shaped coil, two C-shaped coils. In other words, coils like this, the windings here and all the way around again, and then you've got the thing this way.
No, the winding is, in each case, it's winding and it's coming across, and then it's going back and coming across, and it's layers on top of layers.
Right, I'm just wondering what the things above the L2 coil there are, because he's showing a representation of 12 coils.
Yeah, but see, this same wire that you see right here is the same wire that's up here. It just went around the thing. Okay, we go to number 4 there, and it shows another circuit for lighting light bulbs. And we go to number 5, and what you see there, basically, you know that Tesla had this thing rigged up where he could walk around the room with light bulbs, and they would light up. And you have grounding plates on each side of the room. And you have this high voltage generator here, which is running this capacitor deal, which in turn has got a step up into your conventional Tesla coil-like arrangement. These coils are actually not the way you see them. They're wound around each other. And of course that's going on, and that's causing the flux lines in the room to be so heavy that the light bulbs are lighting up without being plugged in. Okay, well, this immediately will tell you something interesting. If a generator can do this, and this is your Tesla coil here, then a generator and an electric motor are really basically the same thing. It's just a slight difference in the way they're put together. So if you can generate electricity and put it into something like this, then you can reverse that situation and you can run an electric motor. So this same circuit here, if you do the right things with it, will run your electric motor for you. And that's basically what's going into the electric golf cart that the California Electric Automobile Association sent me to play with. A group of people out in California are ready to start manufacturing electric automobiles. They want to use the device, and that's the basic, and it's not very complicated. Okay, how are we doing time-wise? We've got about another 5 minutes or so. Okay, we're going to come back to the schematic that you wanted, just to show you for sure what kinds of capacitors. Now, these are just some of the capacitors that are available, and if you read across the see, I'm trying to line it up for you. Okay, one thing you're going to notice on there, that there's a lot of you notice at the top there where you've got kilovolts and kilojoules and that sort of thing. So these are capacitors that you got to be real serious to get involved with. I'm just showing you that they do exist. And
what's their primary use in conventional technology?
These universities like to use them to build for their plasma experiments, and the military likes to use them to build rail guns. And
there isn't a manufacturer's name on that.
Do what now?
I noticed that there isn't a manufacturer.
Well, it's Maxwell.
Maxwell?
Yeah. There are a number of people that make them. This just happens to be one of them. and I wanted you to see that they really do exist. And the dimensions, if you want to see the size, go over to the inches column there. And when you put these things in parallel in banks, you can get a megajoule real quick like. And basically they're temporary storage, that sort of thing. Okay, I guess we say.
With these capacitors, you connect them all in parallel?
Well, just like you would batteries, if you want amps out of batteries, you'd connect them in probably parallel, and if you want...
But how do you reduce the voltage then?
how do you get it down to where you can use it? Okay, well, we haven't got to that part yet. We're coming. That's a good question, and it's one that's going to be answered. Can I move this? Okay, this is what one of those capacitor banks looks like. We're going to see some more of them. This one is 1 kilojoule, I believe. Have you spotted the capacitors yet? That are there. These people, that's all these people do. They build these capacitor banks. They do a booming business worldwide. You'll see some more in a little bit that will probably look more like what you're thinking that they should look like. Well, what you're seeing here mostly are spark gaps, and the banks, those are a different kind of capacitor. There's a picture of one of those. You have the smaller ones and the larger ones, and this is an engineering drawing of those small biscuit-looking things that you're seeing there. You remember the things that look like biscuits that were kind of hooked together? And those are banks of those things. So that's got the dimensions on it, and the physical appearance and everything else if you're used to looking at engineering drawings. Okay, in order to get in this particular group of things, we don't use the Tesla coil, we use a Marx generator. And it doesn't take very many stages of this Marx generator, and it produces actually in the amps and everything are there to begin with. You get very exceedingly high amperage. You get like maybe into the thousands and thousands of amps plus the voltage with this particular type of device. And what you're seeing here, these are engineering drawings of a spark gap. Very high amperage spark gaps. And a Marx generator is composed, this is the schematic drawing of one of these things. So you see basically a Marx generator is a group of spark gaps, very high voltage and high amperage spark gaps with capacitors, high voltage capacitors in between and resistors. And
this slide in your book, in your new book?
I'm going to show you an actual photograph of one of these things next, where you can see it better. And there's other kinds of spark gaps. Now, this is one of the type that we're talking about, and see the spacing between there and there. And it's also got this center deal, which is prevents an overflow if you reach proportions which are dangerous to destroying your spark gap for you. Well, that thing partially unloads it so that it doesn't destroy your spark gap. Because you go to extremely high voltage of amps almost immediately. You don't go through very many stages, so by the time you've gone through 3 or 4 stages or so, well, you're into very high voltage and very high amperage. This is doing the same thing that your Tesla coil does, but in a different way. And the amps are coming at you. I mean, to tell you, they're there, and you've got oceans of them. So with that, we're about ready for another 10-minute break, and we've still got a long, long way to go.
Could you put the March generator slide back up and leave it there during the break?
Say again?
Could you put the last slide back up?
Yeah, we'll start with that and go back through it. You're going to see some more of them. You're actually going to see a complete Marx generator sitting out looking at you and that sort of thing.
In the circuit,
Yeah.
the March generator.
You can actually build one, you know, like that connector block that I showed you that had the capacitor with the resistor for the timing circuit.
Yeah.
If you get a large connector block like that and you get your capacitors and diodes and other things to go with it, well, you can build your Marx generator on the little connector block directly and have a small scale one that still does an awful lot of damage.
Could we see that circuit so we could draw?
Yeah. Okay, several of you wanted to see that circuit for the Marx generator. There's a German fellow came up with this, and back before the war. And you see basically the basic circuit is in the upper right-hand corner, and it consists of one of those spark gaps that we were looking at. And it consists of a capacitor and resistors and other capacitors so as to control the level of energy and direct it so that most of it goes in one direction. And that's one building block there. By adding additional building blocks on it, you up the voltage and the amperage, and it doesn't take very many of them to get into a very high level of energy. And this is used largely in plasma studies, university level plasma high energy studies, and the rail guns, and a number of other things.
It also appears that you can control the frequency of the spark gap.
Yeah, well, you can, by changing the spark gap, adjusting it. I'm going to show you some in a little bit where you can adjust all kinds of things on them. You can control the level of energy that's going forward, control the amps and the volts and a whole slew of other things, depending on how sophisticated the spark gap gets. This one is basically a off-the-shelf sort of thing where everything is already built into it for particular uses, and you'll see the thing all come together in just a little bit as to how the things go. Okay, I'm going to show you a different kind of spark gaps. Okay, I'm trying to get it to where you can see the whole thing, where you can see the dimensions. And those balls that you see in there are carbon balls, and the reason for that is that they don't evaporate like your metal ones do. They have a much higher capacity for electrical current and other types of things. So you'll see that there's all kinds of adjustments on these. For example, by screwing these, you can change the length on it. And on this one here, where you have the 3-dale, one of these is a ground. One of those three, it would be an overflow ground, or one that would control the level of current. Say that you have a great deal more voltage and current coming through there than you want to go forward. By adjusting those things, you can adjust it to the level which you want to go forward. And the size on these things is not particularly large. You'll see in inches down here the description of them. These are actually smaller than the other one. The first one I showed you there was about 9 inches long. So it was quite a bit larger than these. The top one there, You can use these with your Tesla coils also. Any questions on these? You see, these are made to go up to about 370,000 kV, and that is way beyond what you need to get a megajoule or a megawatt. You could almost go into the hundreds of thousands of megawatts with something like this. Okay? Okay, we're going to see a Marx generator, what it actually looks like. That thing in the center there that's round, that's got the device sitting inside it. This is a Marx generator. This is a large metal tube that has a cap that goes on the end of it, and you fill it with oil, very much like the oil that's in your automobile. And the reason for that is that a Marx generator has a lot of plasma display going on around it. You have the ionization of the air and other things around you in such a way that it will interfere with a lot of things. It'll short out the Marx generator, and it create all kinds of interesting electrical problems. So in order to do that, to contain that thing and control it, you put it inside a tank and you fill the tank with oil. And with that, you can get up to a million or several million volts fairly easy from this relatively small device. The measurements on this, this is about a 1.5 foot right there. So you can see that on the end of it. And the length, this one is a very complex one, a very high voltage one. This one probably goes up to maybe 4 million volts or more. So if we were talking about generating electricity, like the number of cycles per second and that sort of thing, and with the capacitor banks and other sorts of things, with the output of this particular device here, which regardless of your input, you have a tremendous amperage going along with your voltage, so you get a huge amount of joules from one of these devices. And it's very difficult to control, and that's the reason why you put it inside the large metal tanks, and you have to pressure it up on top of that. It could be like 400 pounds pressure.
Is the pressure the 20 NS and 30 NS down there on the customers?
I couldn't understand.
Where it says customer furnished equipment,
Yeah.
1,000 gallons of oil and 20 NS, is that?
Yeah, and this is sulfur fluoride, this gas, which you can use either that or you can use the Shell oil that it's mentioning there, or some other similar oil. So you can, the sulfur fluoride 6 thing is a gas.
It's a good insulating gas.
Yeah, it's a very highly insulating gas. And I might mention something else. If you get the dielectric constant of various things, your very highest ones that you normally see are like 8 or 9 or something like that. But it turns out that the dielectric constant for distilled water is about 2,000.
Yeah, it's highly hygroscopic.
It's so high that it's way out of range, which means if you use distilled water and you used gold plates and things in there so that you wouldn't get a chemical reaction, that you could, by using distilled water, you could get voltage that you wouldn't believe. You'll see the dielectric constant here is probably maybe 6 or 7 or something like that, or maybe 8. Okay?
Is that deionized distilled water?
Do what?
Is that deionized distilled water?
Well, I have never actually done it myself. I just know from the University of Chicago physics thing on experimental physics that it lists as a dielectric constant for distilled water is 2,200, I think. And it shows MACA, which is probably one of the highest ones. Otherwise, it's been around 8 or 9 or something. And there's some clays that I know of that go probably 10 times higher than the distilled water. So if you're, depending on the circuits you're building, okay, well here's what's that, the back end there where the hinges are was where we were looking into this device just a few moments ago. Okay, if you want to fix on the size on this thing, these wheels are basically probably about 5 or 6 inches in diameter. The Marx generator, of course, it doesn't take up hardly any of the inside of this thing. It comes that way because if you want to add additional stages to it, that you can go up into the mega joules.
Where's the output on this thing?
The output on it, it would be through some of the things here. They have to be very careful on the outlet on it because the sparking distance on something like 1,000,000 volts there, it creates some real interesting problems. And of course the frequency it runs at and a lot of other things change that. Okay? Okay, some of the test equipment that we're talking about that you normally use on high voltage devices. These things are voltage dividers, and it depends on the amount of voltage they're made to handle. These come in units between 30 kilovolts and 240 kilovolts. They look very similar to the one you see there, except they start getting longer as you get the higher voltage. And they have certain kinds of filaments inside them, and they are also pressured up. You notice the pressure gauge here, and whenever you've got a lot of voltage and current flowing, it also produces some heat, so your pressure thing may change on you while you're working it. But the general idea on this is to get your division on your electrical output down to where you can measure it with your meters. And the type of device that you would end up measuring with would be something like this, and I'm going to show you more details on that in a moment. But this with a proper deal like that can go up to over 1,000,000 volts. But the 1,000,000 volt deal is taller than this room here. This device, and it starts getting it's built up in sections. I'll show you one of those in a little bit. Okay, these are some of the other devices you're often on, switches for high voltages, and those toroids that you see down in the lower corner there come up in sizes up to 52 inches in diameter. And basically what they are, they're a capacitance end that you put on the busy end of your Tesla coil to keep it from sparking unless you really want it to. It's a capacitance device which you load, and it helps you control your Tesla coil and the voltage that's on it. Now, this is the same device with a particular, I'll have to show you, this is not the voltage divider that goes with the 1,000,000 volts. I'm going to show you one of those in just a little bit. Okay, well this has the metal balls and the toroids and things like that. Of course they come in quite large sizes sometimes. The man there with the switching device, that's a high voltage switch that he's working with. So whenever you move hundreds of thousands of volts from one source to another, you have to have a very special switch in order to do it. Otherwise the thing will vaporize on you. Okay, this is the instrument with giving the technical description. It's the same device we've been seeing all along with more of the technical details on it, but you see it does go to 1,000,000 volts with the proper voltage dividers. Is it okay to go ahead? Okay, here's a 200,000 volt one. You notice the 12-inch scale on there. We have a different slide that we'll see the 900,000 volt one, but you can tell that this one has a number of stages on it, and it goes to 200 kV, and this is 120 kV. These are switches, different kinds of switches. This is the instrument with the particular voltage divider that gives you 200 kV peak to work with. Okay, well here comes the 900,000 volt one. You see that it gets out of control real fast like as to the voltage dividers and the instruments that you have to use and that sort of thing. There's actually a much easier way to do this, and since magnetic flux and electrical flux are part of the same coin, it's real easy to measure the magnetic flux with the relatively cheap instruments, hand-sized calculator size deal. You can measure the magnetic flux and you can convert that directly into voltage, and some of those meters that read the magnetic flux actually read in voltage. So if you're, say, 10 feet away and you're reading, say, 200 equivalent magnetic flux of, say, 200 volts at that point, then you have to square the 10, which would be 100, and 100 times your whatever, and then you see immediately that that source had a rather large amount of voltage. You didn't get close to it, you didn't get shocked, and yet you got an accurate reading on it, close enough for whatever you need. So it would be recommended that these high voltage devices that we see there are more of a nuisance than a help, and they're terribly expensive. That meter deal that we're looking at there is $7,000, and the voltage divider things can run up to over $100,000 real quick like, and you can do the same thing with a $35 magnetic flux meter that's got a chart, it's calibrated in volts on the front of it, and by knowing the distance that you are from the source and squaring that times your reading, you can read the voltage direct without even getting close to the device. Because it's a two-sided coin. If you have magnetic flux, you have electrical flux, and they're both exactly related to each other. You don't have more of one than you do of the other. It's this exact copy. Now here's what somebody was asking me about. Yes, I'm going to get it. Whoops. I'd prefer to leave the slide on there. Let's see if we can get the whole thing on there.
Is there some reason you've got that your light aimed off your screen?
Say again? The thing is not squared up here, and that's throwing me a curve because when I try to correct for it, I end up pushing it the wrong way.
Okay.
So that's what has got me screwed up, because when I try to correct the angle, well, I'm going the opposite way. It comes out backwards up there. Thank you very much. Okay.
Use this for your books, it's a little more space.
Well, we're getting far enough along here that we can probably go to lunch after a little bit, and I assume that there'll be a lot of questions also, so whatever. Can you see okay? Okay, I'm going to open the floor at this time to questions, and we'll take off from this device. This is the one which I showed you earlier that had the yellow L3 coil on it, that had the real nice looking metal coil that was real shiny looking. So this is the one that you key on to, and kind of give you an idea as to what some of these things do there. Of course, here's your gel cell battery. Here's a diode that you put on your plus side so that you don't get a kickback. If you get a kickback, it damages your high voltage module. The high voltage module is a laser high voltage source like you'd have in your laser printer or whatever. They're available off the shelf, and if you buy them direct, they're a couple $100 or $300 maybe or something like that. If you're lucky enough to find one in a electronic surplus place, it might be as low as $50 or maybe even lower. So needless to say, I've got pretty good at finding the surplus ones. I burned a lot of them up figuring out how to get things done, and this diode here was one thing that pretty well saves me. It prevents kickback, which destroys your high voltage laser module. It's on your plus side outlet of the battery. It does something else very interesting also. The wire, if the wire here and here is a component of the frequency, which your 6 is there, it loads up like a coil, and the amperage, the current goes towards the battery. The electrons are trying to go that way, and the current is going the opposite direction, which goes to the gel cell. And what is it that charges your battery? It's current. So it turns out that through accident or otherwise, this may not be true of all kinds of batteries, but I know in the case where I have been using the battery for more than a year, and it hasn't changed one bit consistently over a period of a year. So that's a pretty good indication that something is going on there which doesn't match up. And basically what it amounts to, yeah.
I was just curious, you mentioned earlier that that inverter is, the output of that inverter is fed by the output of that 6A coil up there going to the bridge. And you said that that load reduces the output.
Well, what's happened there is that this 6A is detuned so that even though there's a tremendous amount of magnetic flux going on the busy end of the coil there, this 6A is detuned in such a way that it doesn't permit all the power to come through. If all the power is coming through, it would vaporize everything that's downstream from it.
Okay, then it brings it down to some voltage that can drive that inverter.
Yeah, well, you've got voltage dividers. This is a frequency adjust deal here that if you need it, you may not need it. It depends on the input to the diode bridge. The diodes which I use are high voltage radio frequency diodes which show up in your television sets and things like that. And they start at about 25,000 volts and go up. And 100,000 is not uncommon. So you've got, say, 4 of them there at 25,000 volts in the system, and they're radio frequency, and they'll operate very well, say, at 2 megahertz or 4 megahertz or whatever. The particular ones that I've used are 200 nanoseconds, which that would be roughly about 4 or 5 megahertz, or is anyone correct me on that?
5 megahertz is 200 nanoseconds.
It'd be about 5 megahertz. So that's high enough in your radio frequency so that if you multiply 5 million times your output there, you can see real quickly that if your output was even low, like a few volts and partial amps, that all of a sudden you've got something that's much more potent than what it would seem to be.
What size of resistors do you use for a voltage divider here?
Okay, you'll have to determine those experimentally, and again, as we were talking earlier with some of the people, resistors are not necessarily resistors. If you use your LCR meter, you'll find that almost 100% of your resistors have capacitance and inductance. And a lot of times they're much more better inductor or capacitor than they are resistor. In this particular case, the deals which I use here are 220 ohms. They're 1% accuracy and that sort of thing. And it turns out at 220 ohms, they've got about 30 microfarads each. And they've got some other characteristics which change it, but it turns out that, and also these transistors here have capacitance and inductance too. So if you're trying to balance up your impedance on something like this, you can be balancing all day long and a lot longer than that and still not get anything. You've shot yourself out of the water unless you just happen to luck into it, and it gets to be very skillful. Now, the way you get around that is that there are capacitors and inductors and resistors that are actually just that and nothing else. And if you go to your electronic supply and try to buy one, you get very interesting response. I can tell you, because most of them, even though they've been in business for 50 years, won't know that.
Is there some place to start with the value of those resistors?
Say again?
Is there some place to start with the value of those resistors, like number 11s?
On the dividers, these voltage dividers here, what those are doing are correcting the voltage so that when you get downstream, you've got what you need for downstream. You notice there's one on the plus side and one on the minus side. And there's also a capacitor in here to take the ripple out, because when you come through that diode bridge, you've got rippling DC.
And voltage are you dealing with down there in that?
How many volts are you dealing with when it comes out? Well, down here, at this point, you're at 60 cycles and 120 volts.
Before that, back up to that capacitor.
Going backwards?
Yeah.
Okay, well, you have to allow for some degrading, but when it reaches this deal here, the basic deal here is the inverter that you buy down at Radio Shack, which you plug in your automobile cigarette lighter, and you get from 12 volts DC, you get whatever. Now, what I've basically done is tapped out of it and tapped onto this system and put those dividers in there so that everything is adjusted to what you want to have coming out at you.
With a small battery there input, how much output can you get out of that?
This particular one here is about, I think it was about 12 amps at about 120 volts.
And how much is
You could get a much larger amount. You can get, you can probably get 30,000 watts or more out of it.
how much input though? How much?
The input, that's a 12 volt gel cell.
How many? One
So it's doing things which, unless you know what's going on there, can't be done.
Well, it's going to be determined by 3, which is your power supply, because it's going to want to sink a certain amount of power on that source.
There's a lot of things happening there, and you would have to have seen the speech I gave last year, or the book, which has got the details in it, which would explain that.
This is something anybody could build?
Well, anybody should be able to build it, but it doesn't always work out that way. There's not very many pieces there, and the source of those pieces is not very complicated. The only thing on there that would create much of a problem would be that number 3. The rest of it you can get down at Ace Hardware or your local lumber company or Radio Shack. You would think that would be very easy, but I can tell you that after I presented this thing last year, that there were hundreds of people that tried to build it, and there were an awful lot of frustrated people. And out of that several hundred people, I guess, that I'm aware of that tried to build it, there were 6 to maybe 9 that were successful.
This is described in your book.
Yeah, and I can tell you that the PhDs were the ones that flunked out the fastest. the ham radio operators and people like that were the ones that were successful. Yes.
So theoretically, you can take the output of that transformer, run it through a 12 volt converter and plug it back in and replace that battery?
Yeah, we can start all over again. You can put these things in stages and do all kinds of things, but you can actually have a much higher output than this. You can have up to, say, 30 kV from this particular device.
What kind of wire did you use for the L2 or the L1, 2, and 3 on this one?
Okay, the number 7 there is from Barker Williamson's in Pennsylvania. They make professional coil makers, and they were the ones that made the real pretty silver coil. It was one of those earlier ones.
Okay.
And they make them up to 6 inches in diameter and normally about 10 inches long, but you can get them in greater lengths. The larger ones run into like $250 or more each, plus $50 setup charge. The smaller ones, like the one I was using, was about, I think, maybe $40, $50 plus the setup charge. You don't have to use those. You can build your own, though.
What kind of wire did you use for the L1 and the L2 or the L3?
Well, the other windings that you saw on there was basically a 750 volt multi-stranded wire like you would find down at the hardware store with a 750 volt rating. So between the two of them, that would be 1500 volts. So as long as you keep the division there so that only 1000 volts is on each turn, even though at the top you may have 100,000 volts, but the difference between the two of them is say 1000 volts or less. The one that's next to it and that one, say, is 100,000. This one would be 99,000 and this would be 100,000. Well, you're okay. Okay, some more questions?
And spark gap on number 5, you mentioned mill thickness of aper.
I think it was .0025 or something like that, wasn't it? I think it's written on the. I think it's written on the. See, number 5, number 5 there.
This device as you did it, what's the duty?
I can't hear everything you're saying.
Duty cycle.
Can that run continuously?
Oh yeah, there's no moving parts there to wear out.
And you're not dissipating power anywhere in substantial quantity. The only thing I'd be concerned with would be 11 and 14. And
Those voltage dividers, that's going to be tricky because, like I was saying a while ago, the resistors aren't necessarily just resistors.
Yeah, but given the assumption that you have indeed used pure resistance in those locations, dealing with the wattages that you're
well, in the particular instance that's going on here, we have to look out for about, let's say that we got, did I say 20 amps or 8 amps or what?
I said about 15 amps or so.
Okay, well 15 times 100 would be about 15, that'd be 1,500, wouldn't it? Watts.
1,500 watts of energy.
Okay, so that means that on the resistors there, between the two of them, you have to have some way of containing that. So you have to work out the technical problem on that. Now, for the short period of time that I've ran the thing, I haven't, ran it over an extended period of time, just long enough to get a reading on it. Well, it works fairly well. I'm using very fancy resistors, though. They're the aluminum ones that are gold-plated with fins on them, and they're 1% accuracy and all that sort of thing. And they typically, you can get them up to about 500 watts or more, and they do cost a bundle. So.
Well, if you kept 14 low and you kept, I noticed you've got two of them marked 11, one on the left and one on the right.
Well, there's two number 11s and two number 14s.
But it wouldn't necessarily mean that the two number 11s are identical in value, nor the two 14s.
Not necessarily so. What you do, you position them so that by taking off in between them, you've divided the voltage, and part of that goes on, and only the part that you really want to keep goes off.
Yeah, and then at this point, the emitter collector breakdown voltages of your two transistors become
Yeah.
factors.
Well, these particular ones here are, these particular transistors are good to 2,500 volts. They're TO3s.
So you're using flyback type transistors. Kind
Yeah,
of.
they're unusual, quite unusual. As a matter of fact, you'll spend quite some time trying to figure out where to find them
Yeah,
at.
numbers.
Well, they're Motorola, and I do have some numbers, but I don't know whether I've got them with me or not. And with that in mind, there's some other things I need to show you. There is one book which has your timing constants and a lot of other things, and it's the Sam's.
Handbook of Electronic Cable.
Yes,
Formulas.
it's the Sam's book, and Radio Shack used to sell it. Bookstop has copies of it, and it has your basic, all of your basic circuits and other types of things which you need in order to proceed.
Could you just look in front of that and read the ISBN number out of
Surely.
it for us?
Okay, let's see. The ISBN number on this particular book should be right here. Oh, the darn.
On the back label.
I think it's got to be on the copyright page.
Well, I'm looking at the
Probably
main.
really small. Should I come look at it?
Okay, I've got it here. Okay, the International Standard Book number is 0-672-22469-0. And with that in mind, you should be able to get the identical exact book. Now, there's some other books which are quite interesting, and it turns out you would think that there would be all kinds of books on resistors. There's really only two that are in print, and I've got about a half a dozen or more at home that are out of print. But this is one of the ones that's still in print. It's $27, and you'll have a terrible time explaining to the book people what it is you want, because they'll be looking right at the name and the number and everything, and I'll give you an ISBN number on that also. It is somewhat, as far as high voltage capacitors, it's not particularly helpful, but it has a lot of other things in there that are. The ISBN number on that is, let's see, I had it a moment ago, 0-442-01558-5.
Okay.
And this is an interlibrary loan. If you have trouble with getting books that you need, these things are terribly expensive, some of them, and you can spend $80 or $90 before you even blink an eye. And this is one of the university textbooks on the subject, which is commonly used, and it has a lot of nice things in it also.
Well, most major libraries reference a book off the ISBN number for you.
Yeah, well, the way I work it, my neighborhood library is fairly small, but they have a computer system for interlibrary loans, and they're hooked into just about everywhere. So most of the books I get, nobody wants to really read, so there are very few copies of them out there, and they find them real quick, like with the computer. And here comes from City Library of New York, from Harvard University, from Caltech, Topeka and Southern, or whatever, that sort of thing. Okay, some more questions?
Were you going to get into those capacitor banks?
We've still got a bunch more things that we haven't looked at. We're beginning to run out of time. I tell you what, I'll try to switch those into the speech when I do it here the next day or so. Try to remember to put those in it. Okay, we're getting pretty close to close down time, so let's have some more questions and a couple more.
I have just one significant question, I guess, and that is we've dealt with the apparatus fairly extensively and showed commercially available equipment to use in building the apparatus. But I'd like to focus, if we could, on the source.
Sources of those materials?
No, not the source of material, but the sources of the energy.
As to where it's coming from? Okay, basically this goes back to the speech that I gave last year here, where everywhere, all about you, in huge numbers, are electrons. And these electrons basically came from the disintegration of the sun, spewing out into the solar area and became solar plasma. As the Earth spins through the solar plasma, the gravitational field and otherwise pull these free electrons. They're not chemically bound electrons. into the Earth's atmosphere, and the way you know where they are is by the level where your visible light starts forming, and it's like maybe 50 miles or a couple of hundred miles up in the air.
In other words, the solar plasma, which of course also consists of both electrons and alpha particles.
Oh, it's got all kinds of particles there.
Positively charged, yeah, and then you're going to encounter the Earth's magnetic field, and those are going to split or have a tendency to
Most generally, the electrons outnumber everything else.
Okay. And you're going to go into, they're going to go into a cyclotron frequency, right? Because you've got the magnetic field that they're entering,
Yeah.
and they will then process in the cyclotron.
Yeah, well, basically what happens, you end up with your shear zones or your Van Allen radiation belts and various other radiation belts, and those are kind of shear zones where the electrons are being disturbed. So anytime you disturb an electron, when you push it forward, it gives off a magnetic impulse, and when it pops back to where it was, it gives off electrical impulse, and this can go on forever and ever, and that electron is not diminished in any way.
Acceleration or deceleration of the electron causes radiation.
Yeah, when you disturb the electron, you're causing electricity. In a conventional system, you've got your coils and magnets whizzing by each other, and that's disturbing the electrons, and that's where your electricity is coming from.
Is there a particular frequency that seems to be best for coupling that kind of energy source?
Not really. The frequencies which conventional generation is set at are horribly wasteful and very, very inefficient, and I don't know whether that was intentional or otherwise, but if they intended to do it wrong, they succeeded.
Yes. Given the source that we believe we're tapping here, using a tickler, basically.
Yeah, they're just everywhere in large.
Mechanism so that 6A can couple into that energy.
You know, you're basically disturbing the electrons, and the magnetic flux lines are greatest up around 6A there, and so basically none of the electricity from the battery has ever passed through any of those coils. It's just by magnetic flux has transferred and caused the other coils to react in proportion to the amount of magnetic flux that's there.
Maybe someone could do some calculations on what kind of energy or what kind of frequency might be the best.
Well, actually, once you get the magnetic flux going, you can have coils that are not tuned to it that are in that magnetic flux, and they will oscillate at the resonant frequency that they're meant to resonate at.
Yeah,
so you can go from one frequency to another and still have your electricity there, because actually the electrons are not going through your system. They're just being disturbed by the magnetic flux lines of another electrical system, and that goes back to those power triangles we were talking about, where you can use a smaller power triangle to excite, say, a larger one. In your L1, your number 6 there is, say, the small power triangle, and your number 7 is your L2, which would be a larger power triangle, and that's just like in the atomic bomb we were talking about, where you use a small explosion to make a larger explosion, which makes a larger explosion. So that is, if you want to call it, is over unity, because really basically anything that's above ambient is over unity.
Factor there.
Yeah, well, it's squaring according to the law of squares, and you see that in Fibonacci series. You see it in all kinds of interesting things, like in human development, from one little cell and it splits to 2, and then 2 becomes 4, and 4 becomes 16. And by the time you've done this several times, you're to a million of whatever you start out with.
You might be able to look at the prime number series.
Yeah, well, your flux units will become so many of them that you can't believe it. And once those flux units are going, then you can transfer this over to another power source, and it won't diminish the one that's running. The one that's running will just maintain itself, but it will cause the other power deal to activate.
But we are under the assumption, Don, that we are tapping into an energy source here.
Yeah, well, that's the whole story, is
Right.
the fact that the electrons, when you bother them, they give you useful energy, and it's beyond ambient, and therefore the snowball, you've carried the snow up to the top of the hill, the little snowball, and you've turned loose of it, and it's rolling down to the bottom of the hill, and it's getting bigger and rolling faster as it goes.
Do you anticipate dedicating much time to the mechanics of the coupling? I mean, the actual theory, I should say the theory of the coupling?
It's best to think about that after you've got one up and running. The trick is to get one that's up and running and behaving according to what a Tesla coil is supposed to do, and forget about all these other things or where you're headed. Just get the darn thing going.
Don't worry about the miles per gallon.
Once you get that part done, well, then you can start worrying about other things that you might need to do in order to make it useful. Otherwise, you never get there. You'll get hung up on some problem along the way, and chances are you have a fair chance of getting there the first time if you're lucky.
Excuse me, how does this relate to what I've been reading about standing waves in the Earth?
Standing waves, well, the Earth has its own, cycling, has its own resonant frequencies, and as a matter of fact, one of the offshoot inventions on this thing, you know how your MIR works, where you can take pictures of inside people without cutting them up? Well, you have a very large magnet that's coming off and on, and then it's disturbing the hydrogen molecules, and when they spin out of position and when they spin back, they give off an impulse, and you're photographing that impulse. Well, it turns out that the Earth is a very large magnet, and it's pulsing off and on, and with a simple coil of wire, you can do the same thing with the Earth that you do with the MIR, and you can see the rock formations, you can see the tops and bottoms of them, you can tell whether there's fluid in it and what kind of fluid's in it.
Actual devices exist?
It exists.
In fact, Tesla had calculated the Earth resonant frequencies fairly closely. They found out that they were slightly different.
Well, actually, they're quite a bit more than what Tesla did, and I'll tell you how you know this and why. It turns out that the Van Allen radiation belts are one side of a big capacitor, and the surface of the Earth is the other side of that big capacitor. So the Van Allen radiation belts are, the oscillation there is, say, between 2,000 and 8,000 cycles per second. It varies depending on the time of day and a number of other things. So the surface of the Earth starts out at whatever frequency the radiation belts are running at, and it goes down from that. As it goes inside the Earth, the capacitance picks up, and that slows the frequency down, so that by tuning in on these different frequencies as you go down, you listen to the noise level, and that tells you what depth you're at.
A couple of questions. Have they ever done any calculations on with possible interplanetary charge density differences?
Well,
perhaps this planet has a charge difference.
Well, it's very obvious that all your galaxies and planets and everything else all have immense electrical charges on them, and that's what's holding them pretty much in place.
Well, yeah, because just considering the possibility that if you take a sphere such as the Earth and you put a large charge on it, and then you put a charge on another sphere, and say it's a different charge, you're going to end up with a large passive.
Yeah, well, actually, whenever you get hit by a meteor or a comet or something like that, they're coming in, they have a different electrical charge on them. As a matter of fact, part of that is the reason why, say, the space capsule's coming in, when they heat up, the friction, the electrical difference there causes the friction, it's the electrons are banging against each other at such a rate that they're generating heat, and that's where your heat comes from. Okay, we're going to have to close it down. Maybe one more question here, and we'll do that. Did I leave anyone out?
You're going to meet later on today?
Not today, but if you look on your schedule for Mark Hendershalt there, I'll be giving a speech in his place, and I wouldn't be surprised if they don't ask me to repeat this, since we didn't have a real large turnout. Last year we had this room and that room all together filled up on this deal when I gave it.
Do you know if Mark is going to be here this week?
I really don't know. I asked why he wasn't here, and I think someone said he wasn't feeling well or something. I don't know the details. I wouldn't know the details. So, yes?
Question, you said quite a few people built these and you had more failures than successes.
Yeah, and the people got real upset with me. They called me on the phone and just talked for hours at a time, and they were terribly upset. You don't know what you're talking about. You're naive, blah, blah, this and that. And
So,
I said, well, let's see if we can get it right, and then we'll talk about all these other things.
well, if a person done exactly as a plan, it should work, shouldn't it?
Well, if you're lucky enough to get all the things in the right spot, it'll work the first time.
There's a couple of things that would, I see what you're saying. In other words, this is a repeatable process.
Yeah, we're going to have to close it to
It's
take it.
scientific, it should work every time.
We're going to have to close down.
You get into some pretty tricky couplings because assuming.
Yeah, okay, well, thank you, and I'm going to put this up, and this is the end of the speech, and we'll talk about it a little bit. Okay, thank you.
Flux line meter, flux reader, flux media.